now we have George as our last speaker for the session. Please, go ahead.
Hi, thank you for coming today. And let me just say that this is joint work with my colleagues, Rida et al-Mahsen, Mahsa Shirmohammadi, Anton, Varonka, and James Worrell, sometimes known in the community as Ben Worrell. I'm going to explain what a determination problem is and what orbit closures are, and we'll try and leave the kind of difficult mathematics until the very end. In particular, Nikhil just gave a great reachability question in his talk, where he was talking about transitions through a given program. In our setting, that reachability question could be thought of in terms of a finitely generated group of matrices, and then I give you one vector as an input, and I give you one vector as an output, u and v, and I ask whether there's a group element from your finitely generated subgroup such that you can make that transition from one point to the next. So this orbit problem has been long studied. In particular, if you take a general matrix group, the problem is undecidable. But it's decidable in the commutative case. And in fact, from about the early 70s, if you worked with just a cyclic group, so a single generator, you could actually decide this reachability question in polynomial time. So with this idea that actually the problem of reachability is generally undecidable for matrix groups, why not make your life simpler? And by simpler, I mean we're not going to consider orbit questions properly, but orbit closures. So I understand that orbit closures might not be the kind of the most well-known thing today, but they've recently appeared in lots of different papers in the context of, say, the threshold problem, or resolving the threshold problem for quantum automata, perhaps even the equivalence problem of deterministic top-down tree-to-string transducers. And also when you're trying to think about invariance or algebraic invariance of certain looping programs, they all appear in these different contexts. So just before we move on, when I say that it doesn't work in like a commutative setting, what I've written on the right-hand side is the kind of looping program I'm interested in. So these stars, they're going to be non-determinate. You can evaluate these asterisk symbols as either true or false non-deterministically, and within each iteration of the loop, your branches is either going to pick a linear update, so you're taking a vector, you're updating it by either matrix 1, matrix multiplication against a vector, or you're updating it with matrix 2. And then it doesn't matter, we don't really care about the termination of the loop in particular, we're just interested in how it's running. We're particularly going to focus on algebraic invariance in this talk today. So what do I mean by an invariant? This is just going to over-approximate the set of reachable points of your loop program. So I've got there are 3 of the diagrams on this page that have the same system of dots, the top 2 and the third one, or the first one on the second row. And of course, I've drawn a pink set over these reachable states, and depending on what type of over-approximation you allow, you can get different shapes of sets. The next 2 the bottom 2 are the ones that I'm kind of more interested in from our point of view. So one of these just draws like a y equals x or plus some kind of constant line through some points. So this is a linear over approximation. But if I wanted to draw linear sets over the second or the third bottom picture, I'd have to use lots of different lines. But we have a nicer line, this pink looping line, y squared is equal to x squared plus x cubed, which does it all in one simple loop. So somehow we might consider this a better approximation. So just to kind of point out here, I'm going to be interested in algebraic sets. They're just going to be the common points or zero loci of families of polynomials. So they're just going to be polynomial solutions, but in maybe several variables. Here, on this slide, I've obviously done it in 2 variables, but you could do it in as many variables as you like. Now, let's try and go with an example to begin with. So I'm going to give you my favorite algebraic set. I say favorite because I use it on all of my talks. And I'm going to say to you, well, I want you to jump using a dynamical system only on the pink line here. So you could think of yourself as like a rabbit or a frog jumping in 2 dimensions here. That's actually what I'm really asking you to do, is to kind of take an incomplete program, and these jumps I'm going to ask you to be linear. So the elements you have to fill in here are thus a 2x2 matrix and an initial starting point, which will be alpha. And then, so long as you stay inside the pink set, you've got this kind of what we call an orbit, alpha, n squared alpha going through. So this isn't quite the whole problem, though, because if I left the problem statement as it is, you're allowed to choose the trivial loop. So this is kind of a cheating method. Don't do this one. So with one single point, you would obviously solve this problem, which is uninteresting. So let's not do this. I should say that's why the asterisks appeared. We have this kind of maximal notion here. Maximal in the sense that for the purpose of liveness properties, I want to explore the set of, or the kind of specification as best that I can. So let's try and ignore this kind of rubbish solution here. And instead, why don't I give you my favorite solution then? So if I take this particular matrix, 1, 1, 1, 1, 1, 0, and I give you the starting point 1, 0, if you feed your alpha into the set Z, I can evaluate it as 0 squared plus 0 minus 1, but obviously that's a plus 1, minus 1 is equal to 0. Okay, so we've started on the pink line. Great. And then when I do a jump, I might switch to a different kind of fiber or a different line in my polynomial set, but that's okay. I keep flipping back and forth. And what you should notice about this particular kind of variables that are happening here, your favorite linear recurrence sequence might be occurring. That's 0, 1, 1, 2, 3, 5. Going forth. So what I've actually done is I have generated the Fibonacci numbers and the Fibonacci numbers plus 1, so consecutive Fibonacci numbers in x and y. So actually, some of you who might have a mathematical background might recognize that actually the polynomial, this polynomial that appears inside the set Z is actually Cassini's identity, which relates 2 consecutive Fibonacci terms. So all I want to take away from this is that somehow the solution I've given here is the best solution, even though I have left out all, like there are 2 curves I've not even touched in this set. I've actually covered in a polynomial way the entire set as best as I possibly can. Okay, so moving on, like, what if I took this from a mathematical setting, but I said, let's do it in loop synthesis? So loop synthesis being a type of program synthesis, but I'm doing a very specialized case. So we start with our same input, and then I rewrite the problem slightly. I want to now come up with a loop of a specified form, so I just have an input, and then I have a linear update, and I want tightest or maximal, one of these types of adjectives. And why do I call it tightest or maximal? It's because somehow the best choice, or the maximal choice, will be the closure in the Zariski topology. You don't need to know what the Zariski topology is for the purpose of this talk, but it's saying that in a polynomial sense, this was the best choice that we gave. If you're more into your Hoare logic or Hoare triples, then of course I could ask you for a satisfying pair, i.e. some matrix and some vector, such that the 2 Hoare triples at the bottom of the screen are satisfied, and my maximal condition just says, oh, well, I want the best possible polynomial approximation, what we're going to call this orbit closure. So I should say that actually, if I did give you this example and you wanted to compute the best alpha and m, which we did on the previous slide, the tightest complexity that is known appeared in a previous POPL paper last year on strong loop, that considered strong loop synthesis. Strong just being the same as our tightest or best aspect here. Loop synthesis might not be so well known, but you can consider it as the kind of sister or opposite side of the problem of invariant generation. Invariant generation being I give you the program and then I want to automatically find properties associated with it. Nikhil did mention this previously. Loop synthesis goes the other way. It gives the property or the specification and says generate the loop. And you could change this into a decision problem by saying, well, if there is no such loop, you must still output the answer no. Of course, if you constructed a loop, then you should be saying yes. And I should say that there's lots of work, even in just the linear setting. So when I just take linear updates, that might be one linear update in some of these cases. So that would be like where we see the word simple, we mean just a non-branching single path loop. But there could be many different updates. I've already shown you one where I had 2 different matrix updates, and that's kind of the point of our paper today. The paper considers 2 problems. I should say, on the previous slide, I said that this was strong loop synthesis, but you could think about the fact that I only had one single matrix, that I'm actually generating a cyclic matrix group and then applying it to some vector. So I can think of this as the action of a cyclic group acting on a single vector. And we'll call that the cyclic orbit closure determination problem here. And it literally says, okay, I've taken my favorite set defined by polynomials, and I ask whether you can kind of explore this set in such a way that I output a loop. You could also ask the kind of appropriate loop question in this, the analogous group question here. So this is a bit more difficult, perhaps. So now, before I gave you a nice set Z that lived in the plane, now I'm giving you a set of matrices. But this is actually just meant to be confusing to you. Think about what a matrix is. So this GLDQ notation might not be familiar to you. Let me explain it. Here I'm taking D by D matrices, so D-dimensional square matrices. Their entries live in the algebraic numbers, so they're pretty nice to go. And this GL just means they form a group in the sense that they are invertible. So if I have a matrix, I can calculate its determinant. So long as that determinant is 1 or minus 1, then the inverse of that matrix also lives inside the kind of group, and you'll get these nice algebraic numbers. So this is what I'm talking about when I look at invertible matrices. But of course, these D by D matrices have D squared entries. So Z is, when I say Z is a subset of matrices, just think of this as points lying in D squared dimensions. Before you saw it in dimension 2, but now we're working in D squared dimensions. And now I'm just asking, well, if I take a matrix or a set of matrices, this Z, is there a group structure inside them? And in particular for this version, is there a cyclic group structure? So now, you know, we've done away with this kind of alpha part that appeared in the previous loop synthesis. Just the results that we have in this paper, this theorem, says that in the cyclic group determination case, actually you can not only give a decision problem, but you can also output the matrix in the case when your answer to the decision problem is yes. Now, the thing that we're going to go from here is, well, I've put this kind of word in brackets everywhere on this slide, cyclic. So can we do any better? And luckily for being a POPL paper, the answer is kind of yes. Yeah, I know, we're not confident about these things. So previously we were synthesizing, i.e. making different linear loops from before, but previous slides just used a single matrix to go through. Now let's do it for multiple matrices, M1 up to MS. And we ask, when we apply these matrices in a non-deterministic or branching path system, can we do any better in this sense? So that means, can we do this nice over-approximation and give the best possible answer in terms of polynomials? And obviously, when I talked previously about the cyclic group determination problem, hopefully you are all aware of groups that are not cyclic, so there's good motivation for just the general case of this problem too. So again, this notation might look scary to some of you, but this set Z just lives in some large dimensional space, D squared space when I have D things working on it. And we're just asking, rather than a matrix, so I should have said my previous notation here where I had these angle brackets and M just meant I was applying M to itself, or maybe its inverse. So that's why I'm getting this kind of over the top, meaning a closure. Angle brackets is just M, M squared, M cubed, M to the 4, or the inverses. Here I've just got some group G, and really I don't really need the angle brackets here. I can just take the group closure. But the kind of nice thing here is something that didn't appear in the previous slide. Why do we call these determination problems and not just decision problems? And the reason that we call them determination problems is the user also has to give the S, so whether there are going to be S matrices acting on this. So what you're going to do is your inputs, you're going to be given your favorite algebraic set Z. It's always in pink for me. And you're going to give your favorite natural number, and you're going to ask whether you can explore that algebraic set in a way using a group that's generated by S elements. Okay, so the results of our paper say the yes kind of is that we have complexity results in the sense that we have to give a complexity result, I obviously have to give you the full definition of these problems, but that's just parameterizing the problems by saying, well, your algebraic set was defined by M polynomials, and they had certain degrees, and I talk about a zero locus, that's just the set of common vanishing points of that set of polynomials. And I also have to give you the S that I want you to input, and we're living in D dimensions, or D squared dimensions. So the grey boxes are just the hard way of presenting the problems that were on the previous slide, but they allow you to parameterize the problems and then give the complexity output. In particular, all we're saying is that at some point you can get a theorem out of these things. Let's just do one of these problems, or let's just consider one of them. So in particular, oh, there is one last thing I forgot to say. These are the problem statements. The results say we can do it kind of in the sense that we need commutative matrices. We only work in the commutative world. We're not even almost commutative in a kind of nice sense. Okay. I will try and explain where the commutativity comes from, and perhaps I don't have a kind of further work slide, but the whole point is we'd eventually like to get rid of this commutativity problem. The orbit problem, as I said at the start, is undecidable for commutative matrices, but you should always be able to compute orbit closures, but we don't have nice complexity bounds for the non-commutative case. Okay, so what is really happening here? My one last thing then is that there's an alternative way of thinking about what this non-deterministic loop looks like. And because you have commutativity, you can write the kind of, in the loop setting, these bottom two lines are literally just saying, well, what are the matrices that I can apply to alpha? And because you're allowing commutativity, you can just lump all of the M1s together, lump all of the M2s together up to the MIKs, as much as you like. Okay. Without trying to give you the full proof, let's discuss where these kind of bounds come from. So it turns out that, like many matrix problems, you might want to consider a change of basis that works in your favor. For us, we know there is a change of basis such that you can always choose your alpha to have 0, 1 entries. Because there are 0, 1 entries, you're in some kind of finite space, and you're just going to guess alpha in non-deterministic polynomial time. Once you have made the commutativity choice, these kind of matrix groups that live inside this specific general linear sets, they can be decomposed using something called the Jordan-Chevali theorem. And I'm sure I've just mucked up that name in front of a French audience, and I'm very sorry for this. These are essentially what are called unipotent and semi-simple matrices. I won't go into it, but semi-simple matrices, the GS, they are just going to be the diagonalizable matrices. So these sets are kind of well known in the kind of mathematics community, even if they're not necessarily in the computer science community. And the point is you can tease out this nice group structure inside them, and because you put a generator requirement on the underlying group structure, you actually know that these are also going to be finitely generated. The semi-simple matrices in step 3, they have a lattice structure. This just means they act nicely in some arithmetic way. They'll live inside this nice commutative setting of ZK. And again, because we know something about the generators, we can guess the generators associated with these semi-simple matrices in non-deterministic polynomial time. So finally, if all those things go well, you're at your final step and you're saying, well, I've got this Z and I need to know something about gu.gs.alpha. In fact, the GU parts can be kind of tested. If such a subgroup exists, you can check it in the theory of the real closed fields. But our complexity bounds don't come from checking every type of sentence. The sentences have a specific structure going down inside the kind of matrix group. And they have this kind of what's an existential, universal, and existential blocks. But these stars are meant to be blocks of existential operators, a block of a universal operator, and then a block of an existential. So, final slide. We consider 2 problems, group determination and orbit closure. Orbit closure being the one that kind of generalizes loop synthesis that we saw at the very start. And when you parameterize the problems in this very specific way, which I've done in this slide, we have polynomial space procedures for both of these problems under the assumption that the matrices commute. Thank you very much.
Okay, thanks. Are there any questions?
Hi, great talk. You had a time complexity bound earlier. Would you? Yeah, so I noticed that this bound doesn't seem to depend on the number of generators.
Yes, good point. I should have pointed this out.
Yeah, I'm kind of curious if you could give an intuition as to why that might
Yes,
be.
thank you for pointing this out. So essentially S, you can always choose to be the minimal one such that it works. Otherwise, you can just add, say, an identity branch to everything and you're not changing anything. And within the kind of mathematical structure, you know that S must be bounded from above by D, which is the dimension that you're working in. Once you've kind of got that under your thing, you actually only need the D. So it's always good to give the S, but it doesn't matter in the final result.
Okay, cool. Thank you.
No, thank you for the good question.
So you investigated these results with respect to real algebraic numbers. But real closed field is a fairly difficult theory. There are lots of problems when you deal with real numbers. Is the problem simpler if you took complex numbers?
Ooh, this is a good question. So actually, I should say that I even had a backup presented for this. So I said real closed fields, but in fact, the theory that we're doing for the complexity bound also works over complex algebraic numbers too. So luckily, we can actually rely on the same results in this setting.
And maybe it could be even simpler, no?
Oh, that's a good question. Probably it is going to be simpler, but I don't think we considered it in our kind of dealings. But thank you.
So kind of two things I was wondering. One, so you mentioned just for commutative groups. One example I would think of like the most mild thing that could be considered that's not commutative, but also would be very interesting would be like the Heisenberg group. Is that
everyone loves the Heisenberg group.
Because there's also some problems that this would. So like I feel like if you could do the orbit closed, what do you call it, the generation or the orbit problem for the Heisenberg group, plus if you could do it for complex numbers where the kind of invariant you're looking at, it involves the complex variables, but also their complex conjugates. If you could do that, then I think you would solve some hard problems. And so I'm wondering, what is the complication that stops you from doing that?
So in some sense, the Heisenberg groups will have what are called unipotent matrix elements because they are this upper triangular matrices that have ones on the diagonal, which gives us this unipotent/nilpotent structure. And the unipotent matrices are the ones that cause us problems. If you just consider semi-simple, i.e. diagonal matrices, they're the kind of easy ones to tease out because in some if I tell you in advance all of your matrices are semi-simple, i.e. diagonalizable, you can actually choose a change of basis matrix that diagonalizes all of them at once simultaneously. You don't have that kind of fun situation in the unipotent case, which kind of covers your Heisenberg setting. I think also even the orbit problems, so not even these orbit closure problems, are supremely difficult in the Heisenberg case. I would have to check. I know people are interested in the Heisenberg case when you use, say, integers or rational entries for your matrices. We're specifically avoiding rational numbers or integer numbers here because as a backup slide, like the loop synthesis problem, which I considered at the start, is undecidable due to relations to Matiasevich's work. Essentially, you're solving polynomial equations in several variables, and over Q or Z, you either have undecidability or decidability is open. So you've struck a very good setting and definitely a group for us to consider in the future. Whether or not our techniques are strong enough yet, I do not know.
Okay, thank you.
Any more questions? So, if I may have one last one. Actually, I was curious, when I think of orbit problems, I usually think of the other way around. I have the group given, and then I'm trying to find out whether an element is in the orbit, right? But you have the
opposite.
You're finding out the group. How hard would it be to find the kind of the set of algebraic equations that cover, that give you the
so in our paper, we actually divide these two into things. So you're doing what we call an explicit orbit closure problem, and we're doing what we call an implicit orbit closure problem. I.e., in my setting, I tell you the generators, and then I want some so I have some generators. I want to find out some property, and I spit out some polynomials that will then give you the final answer. And I guess the point is that when you work over Q or Z, certain subgroups of the invertible groups in, say, D dimensions have very nice properties. Orbit containment, orbit equivalence are definitely things that have been studied by other people. Whether or not you could kind of translate our results where we're working over algebraic numbers, I'm not so sure, to the kind of explicit versions of the problem that you're asking for. Sorry.
Thanks. Yeah, thanks. This concludes this session. So I think we have a break again now, the poster session. So thank you.